My name is Parth Patel. This is Lab 5, Magnetic Braking. So a little introduction to this lab. We'll be trying to relate the changing in magnetic field to the non-coulombic electric field, which provides a current and an induced EMF. We'll be doing an experiment with the aluminum foil and a bar magnet, and then also using a computer model on GlowScript to compare the values between the experiment and the computer model. So these are some key physics topics and formulas we'll be using in this experiment. Faraday's law is one of them, which is the EMF equals to the derivative of the magnetic flux respect to time, and the magnetic flux equals to the integral of the B field times the n unit vector over the cross-sectional area, and then the change of magnetic flux is reflected by this formula we'll be using in code. And then Lenz's law is just like the derivative of the magnetic flux, but it has a negative sign and a number of coils within it to figure out Lenz's law. So the preview of our results was 1.33 seconds when doing the real experiment when the bar magnet was going through the aluminum tube, and then the ideal was 1.15 seconds on the GlowScript model. These are some additional formulas we were using throughout the class, which now are incorporated into this topic as well, like the Biot-Savart law we've been using since the last lab as well, which is this, and then the change in magnetic force, which we'll be using as well, and then Ohm's law, which is just the ohmic resistor, which we could interpret as the current over the potential difference over the resistance. And then we'll be using Newton's second and third law, which is force equals mass times acceleration, and third law is just the equal and opposite force. So these are some assumptions and model we're doing for this experiment. We're neglecting any air resistance or friction within the tube, and then the magnetic bar is the magnetic dipole force within this experiment. The surroundings is Earth's gravity and the aluminum foil tube, and then the system is the bar magnet. These are the procedures for the experiment. We're basically finding the north pole of the bar magnet using the magnometer app from our phones. We're also folding the aluminum foil into a tube shape if it's not already a tube, and then we're holding it vertically and dropping the magnet through, and then recording the time that it enters and the time that it exits, and we're doing this 5 times to get an average time. So while doing this experiment, this is the initial data on the left here of the tube, and then doing the experiment on the side 5 times, you can see the average was around 1.33 seconds. And then from lab 3, the magnetic dipole was 2.67, but that value is around 65% off from the computer model, so it wouldn't give me a good data for this experiment. So I'm actually using the mean value from that experiment to do the dipole value on the ideal GlowScript model. So the coding, I didn't change much on the coding. I literally just plugged in the constants here and here, and then ran the code. And these other stuff were just constants that I kept in the code from the base starter code. You can see from the graph that the time was actually only 1.158 seconds, a little bit less than what I had. And then you can see from the graph where the gravity is greater on this side, and then when it's in the tube, it's actually equal. And then when it exits the tube, the force of gravity is again increased. So analyzing the computational results, what color of the tube correlates with the direction counterclockwise or clockwise? The red represents counterclockwise and blue is clockwise, and this is found by using the Lenz's law rule. What happens if we flip the magnet? Of course the magnet will still fall, gravity is still there, but the direction of the current will be flipped. How does this affect the real world time compared to the computational model? The computational model was shorter, but it was an ideal model, so it didn't account for things like human errors or air resistance or friction within the tube as well. How does the plot shape tells you about the force acting on the magnet? As I explained it before, before exiting and entering, the gravity was greater than the magnetic force, and then while being in the tube, the magnetic force and the gravity equaled each other. Some possible errors could have been measuring errors, like measuring the time in and time out could have been off by a little bit, and there could have been some contact within the tube between the magnet and the tube. It could have caused friction or even drag going through the tube, which could have increased the time as well. So answering the what if discussion questions, what if the resistivity of the conductor was reduced close as possible to 0? How would this affect the dynamics of the following magnet change? So using Ohm's law, we can see resistivity is proportional to the resistance. So 0 resistivity means 0 resistance. Current's inversely proportional to resistance. So a near 0 resistance would lead to a higher current. So having a higher current, it would mean it would be a larger magnetic force, since the current is proportional to the magnetic force. So answering the second what if discussion question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes allow for more current flow, which affects the overall magnetic force. The induced current decreases. Magnetic force on both objects will also decrease. And the gravity would have a larger effect on the magnet, so it will fall faster as well. So overall, it will be less magnetic force and more gravity contribute to the fall of the magnet. Thank you for watching. Have a great day.